Welcome to MJ's Brain Boost, the only brain boost that actually works. This is the electrochemistry lesson, and we are touching on the very basics of the electrochemistry part. We're gonna focus exclusively on the galvanic cell. All right. The electrochemistry is the branch of chemistry that deals with the interrelationship of electrical currents and chemical reaction. Basically, how we are using electricity or how we produce the electricity, all right, through a spontaneous reaction, and how we are using that electricity to force the reaction to take place. All right, that is the interrelationship of electrical current and chemical reactions. All right, so we've got two types of cells. We've got the galvanic cell and the electrolytic cell. All right, so in the galvanic cell has got two compartments, and this one has got one compartment, and this one has a cell bridge. This one does not have a cell bridge, but I'm going to explain what cell bridge is and what is the function of the cell bridge, especially in the galvanic cell, because today we're going to focus exclusively on the galvanic cell. Does not need a battery, does not have a battery. That this one does have a battery. It means this one is spontaneous, it happens on its own. Okay, does not need electricity to run, but rather it produces the electricity. All right, and then this anode is negative and cathode is positive, and the opposite is true for electrolytic. Then the most important part is you are converting chemical energy into electrical energy. Like I said, galvanic cell is a spontaneous redox reaction, meaning it is producing electricity. The goal is to produce the electricity. This one, you are using that electricity to make sure that the reaction is taking place. And then now, redox reaction is spontaneous. All right. So what does this mean? This means, remember, in galvanic cell, all right, which I'm gonna teach you in greater detail just in a few. But in simple terms, when we have a positive E cell, it means we are having a spontaneous reaction. Please note that in your mind. All right, bear that in your mind. When you're having positive E cell, it means that this reaction is spontaneous. It means a cell can work on its own. It generates the current. But when the redox when the E cell is negative, it means that this is non-spontaneous. It means the goal is to use the electricity to force a reaction to take place. The reaction cannot happen on its own, but it needs the use of electricity to force that reaction to take place. All right. So it means now in an electrolytic cell, what you're doing, you are supplying external energy, okay, from a battery to drive a non-spontaneous reaction. So the cell potential, or the E cell, it will be negative, meaning that the reaction cannot happen naturally. All right. I hope it makes sense. It means you must push the electrons using an external power source from the battery. That is this E cell for electrolytic cell negative, and for the galvanic cell positive. All right. But the similarities is both of them, both the cells, they undergo the redox reaction, and then the oxidation takes place at the anode, and the reduction takes place in the at the cathode. The negative ions from solution are attracted to the anode, while positives are attracted to the cathode. I'll show you how. Electrons flow in the external circuit from anode to cathode in both cells. All right. So I hope everything makes sense. Let's now focus exclusively on the galvanic cell. All right. Let's focus on the galvanic cell. So what's happening is we need to understand a few things. All right. Let's focus on those E cells. All right. Let's focus on the positive and negative electrode potentials. All right. But before we can focus on these, let's firstly discuss these components, all right, about the galvanic cell. All right. So remember, A galvanic cell, it's a device that converts the chemical energy into electrical energy. All right. So when we're talking about the galvanic cell, a galvanic cell, it means this is a device that converts the chemical, allow me just to write E for energy, into the electrical, into electrical, into electrical energy. That is the goal of this. All right, the goal is to produce electricity. And then now, key components that we have is we must have two metal electrodes. We must have two metal electrodes. This is, for example, metal one. All right, metal electrode one. Okay, this is silver metal, and then we've got another metal. This is copper metal. Okay, so these are just key components of a galvanic cell. And then, but now each electrode is dipped into an ionic solution containing its own ions. So each solution is containing its own ions. So the solution one is containing silver ions, and the solution two is containing copper ions. All right. And then now we have a salt bridge, and this is a salt bridge which connects to the two half cells, making sure that the half the cell is complete. All right. Now this salt bridge, it allows ions to move and then maintain the electrical neutrality, and also it completes the circuit. All right. Now we also have got the wire here, and the wire connects the electrodes. You can see this wire connects the two electrodes. Then it allows the electron to flow from one electrode to another. Remember, what did we learn, or what do we know from electrical circuits? We know that the flow of electrons is what you call the electricity. All right, so now you understand the key components, but the other thing that you must always keep it in mind is the electrolyte. All right, is the electrolyte. All right, we have got what you call the electrolyte. So electrolyte, for example, electrolyte, do we always like, we've got so many electrolytes, but we like the nitrate one. Okay, the nitrate one, because we know that all nitrates are soluble. All right, we know that all the nitrates are soluble. So for any given metal, so let's say you're given silver, or you're given copper. All right, they give you copper, then they say, what is your your electrolyte? Then tell them, we gave you copper, then your electrolyte will be copper nitrate. If we give you silver, it will be silver nitrate. If we give you lead, it will be lead nitrate. So always, if they ask you what kind of electrolyte can you use given a particular metal, so say we use the nitrate of that particular metal. All right, so I hope it makes sense. Now I want you to now understand this galvanic cell. Remember, we said that the galvanic cell, we are converting the chemical energy into the electrical energy. All right, into electrical energy. So I want you now to understand something. Remember, we mentioned something about the E cell. All right, so let's have a formula first before we can talk much about this. Okay, sorry about that. So E cell, all right, is equal to the E of the cathode minus the E potential of the anode. This is the formula. That's how you get this. We always subtract the potential of the cathode from the potential of the anode. All right. So now for you remember, we said generally for galvanic cell, you'll have the E potential of negative, of positive, meaning the reaction happens on its own, it's spontaneous. That's what that was for. But you can also have got positive and negative electrode potential in every half cell. Okay, so it means now for each half cell, the electrode potential, um, um, it will show us now, for galvanic cell, for the electrode potential, all right, this E, the electrode potential, it will shows how easily, how easily, um, how easily, or how easy, okay, that shows how easily that have cell gains electron. That's what E cell means. All right. The electrode potential shows how easily that half cell gains electron. It means how easy reduced. All right. So I want you to have this chit chat. All right, or this cheat sheet, that the more positive, E, it's a stronger tendency to be reduced. Okay, it means acts as cathode in a galvanic cell. All right, but the more negative, it means a stronger tendency to lose electrons. It means acts as anode. So it means when you're going to be looking at the standard potential table, you're looking at you look at the half cell that is, if you see the half cell that is more negative, it means it has got a stronger tendency to lose electrons. The one that is more negative, it has got tendency to lose electrons. It means it acts as an anode. All right, but the one that is more positive, it has a tendency to be reduced. It means it acts as the cathode. All right, I hope this makes sense. So for example, let me give you, we can keep them, it's fine. We can keep them, it's fine. Let me give you copper and zinc. Let's check copper and zinc. Copper. Where is copper? Copper. This is copper. Can you see it? This is copper. So copper is plus 0.34. And then let's check zinc. Let's check for zinc. Let's check for zinc. And then zinc here is minus 0.76. All right. Zinc is minus 0.76. It's minus 0.76. So um we said copper is plus 0.34 and the zinc is minus 0.76. So can you see that it means the copper, it will get to be reduced. So if it gets to be reduced, it means it will be cathode. And then zinc get to be oxidized, and then it will mean it will be anode, because we said the one that is negative, it acts as an anode, and then the one that is positive, it gets to be a cathode. All right, then now it means the is for this one. All right, we will say the cathode, we will say from the formula, from the E of the cathode, it means we will say plus 0.34 minus, all right, into minus 0.76. We can do this. I hope it makes sense. All right, and then it means you will have plus 1.1 V. All right, then that's how you you are playing around these things. I hope it makes sense. All right, and then this E cell, which is positive, it shows that the reaction is spontaneous. It means it can happen on its own. We do not need the use of the battery. All right, I hope it makes sense. um Now, I hope everything makes sense. So let's go back to there. All right. Yes, I hope it makes sense. All these things, they make sense in terms of negatives and positives. So in terms of which one is the E potential and which one is the or which one is the cathode and which one is the anode. And another thing, you can also use these. All right, you can also do the number line. We know that the number line has got the 0, and then below 0 we've got negatives, and above 0 we've got positives. So we know we can have a plus 0.34, and then you have got minus 0.76. So we know we can say A, B, C, D, E, F, G, like that. You put these things in ascending order. So you can say A for anode, and then C for cathode. So can you still see that copper, it will be the cathode in this case, and then zinc, it will still be the anode. I mean, there are many ways that you can figure which one is the anode and which one is the cathode. All right, I hope it makes sense. But just know that the more negative we have, it means that act as the as the cathode. All right, in galvanic cell, it means it has got the more negative we have, it acts as the anode. It has got the tendency to lose. All right, it has got the tendency to lose. So I hope it makes sense. So good people, now let's understand what's happening. All right, for example, now in this case we gave you silver and copper. Silver and copper. So before we can even go any further, we need to understand what's happening. All right, let's understand first the redox. So I think I can wrap these things first so that we create space. All right, so let's understand the redox. So in terms of redox, what do we know? We know that redox, it means a reduction and oxidation. That's what redox is. Redox means the other part is a reduction, the other part is a oxidation. All right. So and reduction, what do we know about reduction? It means you remember the old in the olden days, reduction would mean you reduction would mean you are gaining the oxygen, and then oxidate so basically, no, or in simple terms, basically, let's just say gain of electrons. Let me not confuse you with oxygens and with oxygens, right? um um then when you are gain of electrons, it means you are this would happen in the cathode. All right, example, wait, do you see it here? We said when something is reduced, it means it acts as a cathode in the galvanic cell. It acts as a cathode in the galvanic cell. All right. So and then because here you are gaining, and you are gaining, so it means you can also gain mass. All right. And here you are having what you call oxidizing agent. I'll explain these things in greater details. So it means the opposite will be true. Here you are loss of electrons. All right, loss of electrons, and then we see that the tendency to lose electrons, it means it will act as the anode. So this one, it will be in the anode, and then this one, is a loss of mass. Then the opposite is true. This one was oxidizing agent. This one, it will be reducing. This one will be reducing agent. All right. But now you understand in terms of gaining of electrons, all right, gaining of electrons, it means the one that is undergoing reduction, the one that is undergoing reduction, it means the electrons must flow into it. Then the one that is losing electrons, the electrons must come out of it. So let's check now between silver and copper. You can see that electrons are moving from copper into silver. So it means silver is undergoing reduction because it's gaining electrons in it. Then it means silver, it will gain mass. All right, but the oxygen, because the copper, because it undergoing so you keep on breaking it down. You are breaking it down to give you more of you're breaking it down to give you more of the ions into the solution. So basically, let me show you basically what's happening. So you are saying, well, in terms of copper, you are saying, well, I'm having copper in solid, all right. Now, this copper, I am breaking it down so that it gives me more of a copper ions that are getting into the solution. So you are breaking it down. It's undergoing decomposition. All right. So you are breaking the copper. All right. So basically, remember, you are changing the phase. All right. This one, it is in aqueous or in solution. So this one, it was solid. This one, it's in aqueous. So you are changing the phase. So this one was, it means you are breaking this solid to give us more of the ions that are entering into the solution. Then now it means that the metal, what's happening? Because you keep on breaking this metal down. So what does it mean now when you are breaking this metal down? It means it will keep on losing its mass, because you are breaking it down to give you more of the ions that are entering into the solution. So in the end, that's why we're saying the one that is undergoing oxidation, it will lose the mass because you keep on breaking it down. All right. I hope it makes sense. Now, so but um, in that process, it is losing two of electrons. So the electrons, remember we say it's a loss of electrons. The electrons that are lost, they would now need to, they would move because they pile up, 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 and then after that they will start to move. So the electrons, they move. So this is what you call the migration, the ion migration. All right. So we said that the electrons move from the anode, all right, to the cathode. Then they move, they enter this side. When they enter this side, what do they find? They find the silver ions that are already in a solution. All right. So these silver ions, I want to show you what's happening. These are the silver ions that are in solution. And what do they get? They get the electrons that are coming in. All right. These electrons are from the anode side. All right. To give you now to form silver ion. All right. To form the silver solid metal. All right. So it means now this one, you use up the electrons that are coming in. You are using them up to form more of the solid. So it means now this solid, we keep on now. Okay. Like this. With the time, it means you are going to gain the mass. I want you to understand this. So in summary, we're saying in the anode, or at the anode side, you are breaking down the metal to form the more of the ions in the solution. So you are losing the mass. But now, in that case, the electrons are being released. All right. into then the electrons that will move into the cathode side. In the cathode side, you already find the ions that are in solution. Then those ions are going to be used, okay? Those ions, they're going, because they are positive. Remember, according to chemistry, they say unlike charges attract, but like charges repel. So here we are focusing on the unlike charges. You are coming in with positives, with the negatives, and we find the positives in the solution. So obviously the positives, they would need to go into here, okay? They would need to if this is like this, it's like this, ne? We're having negatives that are coming in, so the positives they're going to be attracted here, they're going to be attracted here, the boundary, they're going to be attracted here. Now what do? They make sure that you're gaining the mass. Basically you're gaining the mass because you are forming more of the solid, right? I hope this makes sense. All right, so I hope this makes sense. So here we have, this is half reaction, this is another half reaction, this is half reaction, this is another half reaction. So let's do this, let's do this, let's do this. Let's let me erase this part. All right, so it's fine. Okay, I hope it makes sense. I want to create a little bit space here. All right. So, I want to show you something now. I want to show you something. We're having the half reaction and we're having this half reaction. All right. So let's write them as they are. We're having just that now we know which one is the anode and which one is the cathode now. All right. So I want us to now do what we call the what do we call this? We do what we call the okay, it's fine. Before we can do that, let's look at the function of this salt bridge. All right, I want you to understand something. Remember, we've got the ion migration. The ions are anions or anions are migrating towards the are migrating. Okay, no, let's do this. Remember, in this case, you are let's say we are having, yeah, let's use the nitrate. All right, so what's happening is here you are going to form more of the copper 2 plus in this solution. You're going to form more of the copper 2 plus in this solution. All right, so what's happening is you remember copper 2 plus, they enter the anode solution. So it means now we are having here, you are going to have what we call plus positive charge building up. We're going to have positive charge building up, all right, in this anode solution, because you keep on forming more of this copper 2 plus. So it means positive charges are building up. Then the anions or anions, all right, or anions from the salt bridge, they must counter this build up. All right, because the salt bridge, it's having this, for example, potassium nitrate. All right, we're having, for example, potassium nitrate. So obviously you'd have that, and then you'd have that. All right, so it means here you are having an O3. So it means negative will attract positives. So this one and then this one, they would right. So can you see the negatives, they come, the negative they come, the negative they come. All right, so what do? They so it means these ions from this salt bridge, they must counter this build up of positives. So NO3 minus, which are ions, they must counter this build up. So it means now NO3 and this copper, whatever, they would combine now. All right, they will combine now. So it means we will not have this build up of copper 2 plus, because if we keep on if we did not have any salt bridge, which meant its job is to maintain the electrical neutrality. Otherwise, if we don't have this salt bridge, the reaction will quickly stop, because we'll have the build up of positives, build up of copper 2 plus ions, and then reaction would stop. I hope it makes sense. But on the other hand, the silver plus, they would leave the silver plus, they are leaving what? This cathode solution. All right. So because they are living and they keep on living, they keep on living. What do we have now? We are going to have the build up of negative charges. Here, we're going to have the build up of the negative charges. All right. So it means now the positive part from this salt bridge must come. All right, cations, they must come, and then now counter the build up of the negative charge in this cathode, in this cathode solution. All right, I hope it makes sense. So that's why we're saying the salt bridge, its job is to maintain the charge in neutrality. So you can see the positive, this positive, okay, this positive. Like I told you that we would have this and that. So this is going into the anode, all right, then this is going into the cathode. All right, this one, it will combine with the negative build up, and then this one with the positive build up. All right, copper 2 plus, like that. I hope it makes sense. I hope it makes sense. So this is the job of the salt bridge. It makes sure that it maintains the electrical neutrality, and make sure that now we do not have charge build up, because otherwise the reaction will quickly stop. I hope it makes sense. Now, the other thing that we need to focus on would be the what we call the before we can talk about cell notation, let's talk about um the what do we call this, what do we call this balancing. All right, balancing. So we are having the anode. All right, we're having the anode and the cathode. So we always say, all right, these are our reactions. We will say, well, we're having the, all right, let's do this first. Let's do this first. Um, I want you to see it. What's happening? I want to go back to that potential cell. Um, doesn't want to go back. It doesn't want to go back. I don't know why. All right. Okay. Because I wanted to go back to where I'm showing you the but you know what? It's fine. It's fine. It's taking my time now. It's fine. Let's try the to balance this. All right. So before we can learn about that, let's first do this. Let me erase this so that we can have space. Yeah, so let's do this. Before we can do that, I can we can do a cell notation. I can do cell notation. So cell notation is what you call shorthand. All right, is what you call shorthand for describing a galvanic cell. All right. So cell notation is we're basically writing this. All right. We are basically describing how we are seeing this. All right. So when we are writing the cell notation, is we must always have the um the the um okay, let's start from here. All right, we must always have the what do we call this? Why am I even forgetting this name? What do we call this name? Um, um, what is this, man? All right, let's do this. We say, let me give you the formula, all right, in simple terms, so that we can save time. We can say we can have the elect electrode can have electrode material, and then after this one we have the aqueous species, and then we have a salt bridge, then we have got the aqueous species, then we have got the phase, and then we have got electrode. We have got electrode material. All right. So this one is the phase change boundary. Okay, so it is showing that we are moving from aqueous into the solid. So here we are moving from solid into the aqueous. So it is, even this one is still phase change boundary. All right, and then this one, it basically represents the salt bridge. This one, it represents the salt bridge. All right. So here you'll have the anode, and then here you'll have the cathode. All right, and we know that in the anode, what's happening in the anode? In the anode, we know, we have learned that in the anode, that's where we are having oxidation, and that's where we are having loss of electrons. And then we know that in the cathode, that's where reduction is taking place, and that's where you're having gain of electrons. All right, I hope it makes sense. So we can now try to write this now. All right, we can try to write this. So what's happening is we need to write this. All right, we need to write this in such a way that we are following this order. All right, so what is the anode in this case? Our anode in this case is our copper. Our anode in this case is our copper. So it means now we are having copper like that. It's our anode. We start in the anode side, all right, which is solid, but we are having the phase change. So this copper, all right, this copper solid, we broke it down to give us a 2 plus copper ions. All right, we have 2 plus copper ions in aqueous. Now it's messy. You know what, let's write it here. Let's write it here, because now it's messy. Yes, I hope it makes sense. So we are having copper solid, then we took that copper. So we always start with the that's why I'm saying we have to understand this formula, so or this method of doing things. So we are having copper, and that is in solid, and then this is phase change. So phase, we are changing from solid into aqueous. So copper, we are breaking it down to give us 2 copper ions, okay, or plus 2 copper ions, okay, in aqueous. I hope it makes sense. This is what is happening. But between them, we are having the salt bridge. Okay, so it means this one, okay, here, from here, it's what we call anode half, cell. Then we're having salt bridge. Here we're having salt, we're having salt bridge. Then we are into the cathode half cell. So in the cathode half cell, what do we get? We found the silver ions already in solution. We found the silver ions already in a solution, and then they gained, they received the electrons, and then they converted that into a solid. So basically, you are just explaining, when you're doing cell notation, you are just writing this process in words. All right. So then now this one, it will be the cathode half. This one will be the cathode half cell. That this one will be the cathode half cell. All right. Now, it means we will say, because we're having the cathode half cell in this case and anode half cell, the half cell, then you would say this is the cell notation. This is what you call the cell notation. So like I said, when we are doing this cell notation, when we're dealing with this cell notation, we are following the anode, and then we're having its aqueous species, salt bridge, aqueous species, and electrode species. All right, the cathode electrode material. So I hope it makes sense. Now I want us to let's I think now it's too messy. Let's do this. All right, then we can erase these ones. Um okay. All right. Now we want to now balance this. All right. Um we said copper. You said copper. All right. So let's balance these things. So we said copper. Where's that reaction? So copper is copper. Okay. Mm, all right. Got the reaction by head. Now we said copper in copper in solid. It will give you copper 2 plus 2 of that, and then that's the anode. All right, and then we have got the cathode, and then we've got the cathode, then the cathode we have got Ag plus E, then it gives you Ag silver. Then we want to find the formula. So that's what you call balancing. All right. So before you could do anything, you need to make sure that these things they are well balanced. All right. These things they are well balanced. So if you can check, we've got 2 electrons, but here you are having 1 electron. All right, so this thing is not well balanced. All right, so you multiply both sides by 2. So here you'll have 2, here you'll have 2, here you'll have 2. Then now this thing is balanced, so that now when it's balanced, this part and that part, they're going to cancel each other out. Then what you have, then it means you'll have copper. So you write whatever that's remaining in your left hand side. Then you have got 2Ag plus, and then this side you'll have copper 2 plus 2 Ag in solid, and then aqueous, and then aqueous. All right. So when they say write what we call the net reaction, when they say write what you call the net reaction, it means they're telling you that please make sure that things they are balanced. Then now when they are balanced, you can write that. All right, I hope it makes sense. So let me give you the last example. For example, looking into, let's look into, um, let me give you, say, zinc and copper. Let me give you zinc and copper. Let me give you zinc and copper. Let me give you zinc and copper. I can run this so that we have space. Um, yeah, let me give you zinc and copper, and I think this will um, sum up everything. So let's say you are having, all right, let me say, um, you know, embedded drawing. So let's say this is our wire, and then we've got semi-permeable membrane, salt bridge. All right. Say this is say this is copper, say this is zinc, and then let me give you the solution, or the all right, let me give you the electrolyte, um zinc nitrate, and then here let me give you copper, let me give you copper nitrate. All right. I hope now you understand the job of the salt bridge and other things. We just want to wrap things up with now another thing. All right. So I wanted this to give us um um doesn't allow me to do that. Let me check. All right. Okay, let me just discard them. Yeah, I want this. So let's check where copper is. Copper. Okay, this is copper. All right, copper. Now, can you see? All right, I wanna write it this way as it appears here. All right, copper. All right, I see it. Then with zinc. Okay, zinc is here. I see it. All right, then we can go back to that side. All right. Now, as they appear that side, we saw that zinc is like this. Um, it was zinc 2 plus, it was exactly like this. Then zinc, then the set is minus 0.76. And then for copper, what did we get? For copper, we found something like copper 2 plus, and then mm, plus 2 electrons, and then to give you copper in the solid, and then we said is 0.34. Yes. So I want us to first determine which one is the anode and which one is the cathode. I want us to determine that first. All right. So, what did we learn? All right. What did we learn? We said, um, um, when we are having, when we're checking this, the one that is more negative, it means it's having the tendency to lose the electrons. All right. It means it will be it's having the tendency to lose electrons. So now, what will we say? Okay, we'll say, well, we now understand which one is the anode and which one is the cathode. All right. And I also said you can also use, say, 0, say minus 0.76, and then say is plus 0.34. All right. And then I said you can say A, B, C, D. All right. And then this is cathode, this is anode. It means now the zinc is anode. It means zinc is anode, so it means we will say this is anode, and then this one, it will be cathode. All right, it will be cathode. So we always say, when you are writing the net reaction, the cathode, you leave it as is, then the anode, as it appears there in the standard, you just swapping it. So the anode, which is this one, you are swapping it now, so it means it will be zinc like that, into zinc 2 plus, and the aqueous plus 2 of these electrons. Right, and then now you are having now the copper 2 plus, you write it as is. All right, and then 2 electrons that, and then copper in the solid. All right, and then let's make sure it's balanced. It's balanced because we're having 2 electrons here, we're having 2 electrons on the other side. So these electrons, they will cancel each other. So the job is to cancel these electrons. Now write the net reaction. So you're having that plus copper 2 plus, then the aqueous, then to give you zinc 2 plus, aqueous plus, copper that. I hope it makes sense. I hope it makes sense. So that's the net reaction. But if you are including the nitrate, for example, then you'll get something like this now. All right, because in this case we do not include the electrolyte, so you are reacting them with that. Remember, it's like you're having copper 2 plus and then reacting with NO3 minus. So this one, it will come here, and then this one, it will come there. Then this one, it will be copper NO3 2. Okay, that's how we are reacting them. So it's like I can also where I see this part, where I see this, I can put copper NO3. All right, it depends on which one, which weight you prefer. Then it means this one, it will be zinc. All right, zinc nitrate plus copper solid. So that's how we write the net balance reaction. All right, and then now let's write the what do you call that? The cell notation. We start with the anode. So we see that the anode, so in the anode, so we said is the zinc. So is the zinc. All right. So it means this zinc, it will keep on breaking down to give us zinc plus ions. All right. So it means this is zinc in the solid. Okay, and then we have in the phase, this shows that we are changing the solid into the aqueous. Then this will give us 2 plus, and then we are having that will be in the aqueous. Then we're having the salt bridge. This is our salt bridge, and then we already find the copper 2 plus in a solution. So this copper 2 plus in a solution, we're having already having copper 2 plus in a solution. Then the this copper 2, they're getting the electrons, they're getting 2 electrons. Then now they're going to convert this into copper in a solution. So this is cell notation. And then if so basically that is that. I can give you so many examples, but basically that's how you are dealing with these things. All right, then let's write the E cell. Let's write the E cell. So we know that the E cell is equal to the E of the cathode minus the E of the anode. So which one is the cathode? Cathode is copper. So you'll say is 0.34 minus which one is the anode. So the anode, um, the anode, um, the the anode is this, where is it? Yes, this one is minus 0.76. All right, so if you punch that on your calculator, you'll get 1 plus 1 volts, and then it's positive. And then we said if they were to ask you what does this mean, it means the positive would mean this is spontaneous reaction. This shows that indeed this is the galvanic cell. All right, this shows that indeed this is a galvanic cell. I hope you're getting the gist of this. All right, I wanted to keep this session as simple as I can, and I hope I've explained a lot of things, and I hope I've explained a lot of things. And then now, last part that I want to explain is the what do we mean when we say something is oxidizing agent and reducing agent, and what we call the standard cell. All right, I hope you getting that. So let's wrap this, and then let's do that last part, and then we can call it okay. All right, so which one does it want? All right. Mm, good. So let's learn about the oxidizing agents and reducing agent and standard cell, and then yeah, we can cut our lesson. So what's happening? Remember, we have already learned about the anode, the cathode, and other things. All right. So I want you to familiarize yourself with what do we mean when we say something is oxidizing reagent, and what does it mean when we say something is a reducing reagent. All right. So right, oxidizing agent, and then reducing reducing agent. Yes. So good people, in simple terms, all right, in a redox reaction, oxidation and reduction, they always happen together. All right. Okay, but it means one substance loses electrons. All right, one substance loses electrons, we say it's oxidation, while another gains electrons, we say it's a reduction. All right, I hope from that oil rig memory trick, that is, oxidation is a loss of electrons and reduction is a gain of electrons. That's what we learned. All right, but now we want to understand first, what does it mean when we say an oxidizing and reducing agent? All right, oxidizing reagent um, causes another substance to be oxidized, but it is reduced itself. All right, so it means it gains it means it gains electrons. I hope it makes sense. So causes another substance to be oxidized, but it itself it gains electrons. All right. Now, mm, what about reducing reagent? Reducing agent causes another substance to be reduced, but it is oxidized itself. What do we mean? It means it will loses electrons. So it means reducing agent, it loses electrons, and then oxidizing agent, it gains electrons. So the agent, all right, it means it causes something. So oxidizing agent, what it does, it causes oxidation to take place. But what happens to it is reduced. All right, is reduced. It means itself it gains electrons. All right, so you can say oxidizing agent oxidizes others but get reduced itself, and then reducing agent it reduces others but get oxidized itself. That is the trick that I want you to remember. That reducing agent, it reduces others. All right. Remember, it's an agent. All right. It facilitates things. When we say we are agent, it means you are being sent. All right. So reducing agent is sent to reduce others, while itself it gets to be oxidized. Then oxidizing agent is sent to oxidize others, but it gets to be reduced itself. All right. Let's go back to the example that we dealt with just recently, the copper and zinc. All right, the copper and zinc. So we okay. So let's do this. We have zinc plus copper 2 plus to zinc 2 plus plus copper. All right. So zinc loses 2 electrons. Let's focus on the zinc. All right. Let's focus on the zinc. Okay. Zinc loses 2 electrons. So as it loses 2 electrons, that is what you call oxidation. Okay. So it means zinc. What is it? Is the reducing agent. All right. But now, on the other hand, copper, what does it do? Copper, it gains 2 electrons. Copper gains 2 electrons. So copper gains 2 electrons. It means it's undergoing reduction. So it means copper is the reducing agent. Okay, copper 2 plus is the reducing agent. I hope it makes sense. All right. So it means now in simple terms, as we are wrapping things, ladies and gents. So if a substance All right, let's summarize this. All right, so we say if a substance, okay, if a substance loses electrons, it will be oxidized. All right, then we say it's a reducing agent. But if a substance gains electrons, it gets to be reduced. Then we're saying it's an oxidizing agent. Okay, so that is the trick that I want to I want you to always think of this. And then last but not least, let's focus on what we call the electrode potential. Okay, so we can wrap this one and then focus on what we call the electrode potential. And then this will be the last thing that we're going to touch today. Remember, we are dealing with the very basics of these things. We're just introducing you to the concept of electrochemistry. All right. All right. So let's deal with the last part, which is what we call the standard hydrogen electrode. All right. People would like to call it she. All right. Standard hydrogen electrode. So let's remind ourselves what is electrode potential. All right. So electrode potential, when a metal is placed in a solution of its ions, for example, you saw that we placed silver inside a solution having silver ions. So a metal is placed in a solution of its ions. All right. So a potential difference forms between the metal and the solution. So we'll have the potential difference between the metal and the solution because some atoms lose or gains electrons. All right. So this potential difference is called the electrode potential. I hope it makes sense, good people. So, but why we need a reference material? All right. We cannot measure a single half cell potential directly. It's not possible. We can only measure the difference between the two half cells. Therefore, a reference electrode with a fixed potential must be chosen, and scientists worldwide, they chose a standard hydrogen electrode. All right, and then that this standard electrode, okay, has a value of all right, has a value of 0.00 volts. All right, but when they were constructing this standard hydrogen electrode, there were some conditions. So let's deal with those conditions. All right, let's deal with those conditions. Number one. All right, um you must contains okay, of hydrogen ions. Okay, usually um from hydrochloric acid solution. Okay, that is the first condition. And then we must have a platinum electrode coated with platinum a platinum black. All right. Why? Why platinum? Because platinum is inert, does not participate in chemical reaction, and conducts electrons easily. So platinum, it's inert, does not participate in chemical reaction. It means it has got 8 electrons. It reach its octet state, all right, and it conducts electricity or electrons easily. And then our hydrogen gas is bubbled. Our electron gas is bubbled at 1 atmosphere pressure. Okay. And then we must everything it happens at a temperature. The temperature must be kept. The temperature must be kept at 25, the standard temperature, 25 degrees, and we know 25 degrees is like 280 kelvins. All right, so the conditions give the temperature at 25 degrees, and then and this concentration, all right, and this concentration, all right. So these are the conditions. I hope it makes sense. All right. Concentration of ions, it should be that. Then we are having basically these are the conditions. So let's try to draw that. So you will see that you will have the hydrogen gas bubbled in, and then in here you'll find the platinum. Find the I'm not good at drawing. I'm not good at drawing, but you can go and check the hydrogen cell. I'm not good at drawing, but like, yeah, something like that. Something like that. I'm not good at drawing. All right. So you are bubbling the hydrogen gas. Okay. At one atmospheric pressure. All right. So I just want to teach you how it works. Okay. So if you were to connect another half cell to this standard potential, all right, with the known E cell, okay, so or electrode potential, the potential difference, it can now be measured because we know another one. So it means the measured value tells how easily the other electrode gains or loses electrons compared to the hydrogen as a reference or as a standard. Okay. So I hope it makes sense. I hope it makes sense. So we are always comparing these, and so you can connect zinc here, you can connect copper. It doesn't matter. All right, it doesn't matter. So for example, if you connect hydrogen standard potential with the copper, so you know copper voltmeter, it would read as 0.34 volts. All right, so it means when you are, remember hydrogen, hydrogen, it does hydrogen when losing electron, again hydrogen has got one valence electron, so when it's losing electron it's still happy, and when it's gaining electron it's still happy. So that's why they choose hydrogen to act as a standard. So it means whether it's losing or it's gaining, it does not feel anything. All right. So when you are connecting it, so when you're connecting it, to example, to copper, so it will ask copper, what do you prefer? And then copper says, well, when I'm with you, I'll prefer to be reduced. All right. But when connected to zinc, remember we are having 0.76 volts. All right. So zinc will say, hydrogen will ask zinc and say, zinc, if I'm with you, what do you prefer? Zinc says, but now I get to be oxidized easily. All right. That's why my E cell, all right. That's why my E cell is that get to be oxidized easily. So I hope it makes sense. All right. So just know that if, you must know the conditions. All right. You must know the conditions of this cell. All right. Because they're gonna ask you in the exam. All right. And I've already told you that positive positive E potential, it means electrons gains electrons. Electrode gains electrons. That is the reduction, and it acts as a cathode. But negative one, it means electrode loses electrons. That is oxidation, and it acts as the anode. I've already mentioned that with you. All right. So then now we can let's compare. For example, if you're having hydrogen and copper, so we know we said E cell, okay, is the E of the cathode minus E of the anode. All right. So I want you remember in this case, let's compare. What can we compare? We are comparing, let's say, the the copper and the hydrogen. Remember, now hydrogen asks this one that this copper, that copper, what do you prefer? All right, what do you prefer? And then copper says, well, I easily get to be reduced. All right, I easily get to be reduced. So it means if I easily get to be reduced, it means you know what I prefer. Then copper is then what do we call this? Then hydrogen would say, then hydrogen will say, well, okay, it's fine. Then whatever that you prefer, now I will take along. Then if you were to substitute that here, remember for hydrogen, you just put 0, and then for that, all right? So for example, you would say plus 0.34, because this one, it says I get to be reduced easily, and then into that, all right? So um so this will just be plus 0.34. So you're always comparing that with the standard potential. All right, with the standard one, which is having 0. So I just wanted to introduce you to everything all together. Just wanted to introduce you to you everything, so that you are familiar with the concepts that are used in electrochemistry. All right. So as we are wrapping this up, we said we must have a conditions. So the conditions, the first thing is we must the standard conditions is we must have the temperature at 25 degrees Celsius, or 298 Kelvin. This is the room temperature. All right, this is the room temperature. These are the standard conditions. So this is the room temperature, the first standard condition, and we must have a concentration of 1 mole per decimeter cubic. So the standard conditions, okay, let's write them here, and then we can standard conditions that they will ask you in the exam. So is you must have the temperature of 25 degrees, or 298 25 degrees Celsius, all right, or 298 Kelvin. All right, this is the room temperature, and you must have the pressure of 1 atmospheric. Okay, all right, or this is the same as you saying 101.3 kilo pascal. All right, all right, like that. And then, or you must have the allow me just to write concern. It must be 1 mole per decimeter cubic. These are the standard conditions. So these are the standard conditions that in the exam they might request from you. So ladies and gents, I think this we can just stop here. I think we can just stop here. Yes, I think we can just stop here. We've covered the very basics that we have in the galvanic cell, and you always know what I'm about to say. Until next time, cheers.